understand the YMCA. YMCA.
Manny, this is no place to jam without a drummer. Hey guys, so on this one we're going to be doing multi-degree freedom systems. We're going to be doing the linear plant this time. You can count up how many different degrees of freedom do you think this system has, Manny? Right, there's actually 3 degrees of freedom right now. And so what we're going to actually do though is look at only 2 of them. We're going to control the input of this part of the system with the sinusoidal input, and then look at the outputs of these 2 parts of the system. Now, when you have 1 degree of freedom, you have 1 resonance frequency, but when you have 2, how many different modes of resonance do you think you have, Manny? No, Manny, that's not quite right, actually. No, it's okay, it's okay, it's okay. It won't affect your grade. It's only actually 2 forms of resonance, but the third thing is actually absorption. I'll show you right here as I demonstrate with my hand. Do not try at home, kids. First mode is as we increase the frequency of our input, these 2 things will move together with a high frequency, or high amplitude rather. And somewhere in the middle, this one's going to cancel out because these will have destructive interference while this absorbs it. So that's called absorption, where the amplitude of this is the lowest. And after that, eventually, these 2 will oscillate opposite of each other, and that's called out of phase resonance. So there's 3 different behaviors we're going to be looking at. We also have a damper on here, which is important. That's why this is essentially what's being absorbed, and this kind of acts as our absorber. So after we do that, what do you think we're going to do next, Manny, that we need to know about our system? Not quite. What else did you think we might have to do next? Yeah, that's right. You have to know what parameters you're going to put into your simulation. So make sure you measure each of your masses, and we're also going to be able to, you can take apart your springs using this little guy here, this little screwdriver, and place them on here to do a Hooke's law test with dropping different weights on it or different masses. There's a couple in here. You can look at the spring deflection and calculate your spring constant. Manny, how do you think you're going to get calculate the mass of the cart and the damping constant of this air damper? What would you do? Yeah, well, that works too, but I think the best thing to do is to do a free vibration. So if you take this Allen wrench, you can actually lock these bumpers here in the back, tighten these, bring them in, and that'll actually lock each of these masses. And there's instructions in the PowerPoint to do a free vibration, and you can do a free vibration of this one by just letting it go like we did in the Common Lab, let it vibrate. And we can calculate the damping constant from this and also the mass of the cart, which we can probably assume to be the same between the different systems. Once we have all our parameters, not only can we use the science suite via our ECP software, we can do a free vibration and then use all the data to do a simulation and compare that with our experimental data. How do you feel? Great. Well, we're going to move on over to the rotational system, and I'll show you some of the differences there as well. So this is a multi-degree freedom rotational plant here that we're going to be using. Very similar concept. We're actually going to generate a sinusoidal signal, input signal here, and move this back and forth, and look at the response of these 2 parts of the system. So there will be actually only 2 degrees of freedom. Now you might ask, where are the springs in the system? Well, actually, fun fact, pretty much everything in life is a spring or can be modeled as a spring. But these 2 steel rods are actually going to resist the displacement in the rotational direction, and that's going to act as our spring. So you can use a free vibration to either get the spring constants, or you can also use mechanics of solids, if you remember from that class. There's an equation to generate the spring constant for these steel rods. Another thing to keep in mind is the only difference really is instead of dealing with masses that are going to be used moved linearly, we're actually using mass moment of inertia. So you have to calculate that using the parallel axis theorem, and also what you might know about the mass moment of inertia for cylinders or disks as well. Manny, what's your guess for what the mass moment of inertia is for a cylinder? Right, 1/2 mr squared. Manny, you have anything else to add to our experiment today?